Welcome everyone to the Emerging Technologies Information Sessions 2025 webinar series. My name is Sam Semino and I work for the USGS and the Pacific Northwest Aquatic Monitoring Partnership. And over the last year or so, I've helped put together this ETIS webinar series with the help of a planning committee, but we didn't start from scratch. The Pacific Northwest Aquatic Monitoring Partnership and the Pacific States Marine Fisheries Commission's StreamNet program have been hosting iterations of these emerging technologies conferences and webinars over the past 14 years. And we usually do them about every other year. The aim of this project is to bring together monitoring professionals, project managers, data collectors, data managers, and data consumers to showcase how they implement the latest technologies in aquatic monitoring. And this year's webinar series will take place over the next 5 weeks, like I just mentioned, starting today, with these 2-hour sessions every Wednesday, 9 a.m. to 11 a.m. Pacific Standard Time. And today we kick off the series with the modeling and analysis session. As you can see here, these sessions are all being recorded. So if you can't make a session, you can check out the recordings. These will be put up on the PNAMP YouTube channel. If you go to YouTube, you can search for PNAMP, P-N-A-M-P. And then there'll be a library of these ETIS, emerging technology videos. And they'll typically go up within a week or so of each session. And now I'm going to kick it off to our moderator today, Meg Detloff.
Hey, everybody. Good morning. My name is Meg Detloff. I work with Sam at USGS and PNAMP. Thanks for joining us for the first session of ETIS webinar series. Before we get started, I'd like to go over a few meeting logistics. Next slide, Sam. On your screen, you should see some of the commonly used icons in Teams. Unless you are speaking, please turn off your camera and microphone. If you have questions or feedback, please use a chat function or raise your hand and unmute yourself. We can mute you, but we cannot unmute you. We're recording this meeting and it'll be available on our YouTube channel, like Sam said. A couple of additional troubleshooting tips. If you have trouble with Teams functionality, try leaving and joining the meeting again. Use a different browser. Edge usually works better than in Teams than Chrome does. Or try using a desktop version instead of the browser or vice versa. If you don't have access to the chat, please feel free to unmute yourself and comment and ask questions. That's not a big deal. You don't need to be shy with us. Slide, Sam. PNAMP commits to fostering an open and welcoming environment free from harassment and discrimination, so please remain respectful. Next slide. All right, let the fun begin. Just a note, after each presentation, we'll have a 10 minutes allotted for questions, depending on time. And if we have extra time at the end of all the presentations, we'll open the floor again for questions on any of the presentations. And I'm going to hand this over to Ben. And while he's getting set up, I'm going to introduce him. So I have the honor of introducing Ben Staton. He's a quantitative fisheries scientist for the Columbia River Intertribal Fish Commission, where he started working in 2019. His interests are in the development of quantitative tools and statistical models that maximize utility of data sets while also acknowledging their uncertainties and limitations. His graduate studies at Auburn University involved assessment and management strategies for Western Alaska Chinook salmon, and at CRIPFIC, he has worked on life cycle models, relative reproductive success analyses, and quantifying drivers of imperfect detectability in snorkel surveys. And with that, the floor is yours, Ben.
Okay, great. Thank you, Megan. And thanks for reading that mouthful. I did not quite realize how much of a mouthful all that would be when I provided you that bio. So I appreciate that. Well, yeah, as Megan said, my name is Ben Staton. I'm excited to be here today and talk about this topic of GitHub. And I want to just give a little disclaimer right at the front of this, that this is going to be much more of a what and why about GitHub, much less about a how-to. So If you're here to get a how-to tutorial, this is not really going to be too much for you, unfortunately. But luckily for you, there might be an upcoming PNAMP seminar about that is going to be more of a hands-on type tutorial. But stay tuned for more details on that. But so just to dive in, we'll get going here. So version control, that's what GitHub is all about. So what is version control and why would you want to use it, especially in the context of a data analysis project? So many of you might have seen this comic over here, or have experienced it yourself. You think you have a final version, you always have to append on additional titles and everything, all the while keeping each copy of each of those files as it moves forward. So that's something you might want to avoid. Data analyses are a little bit different because it's not just a single Word document like is shown in the comic. You're going to have multiple code files, multiple data files, all stored within a single directory or folder on your computer. And that is what a data analysis project looks like, or it might have multiple directories, multiple subdirectories, those kinds of things. And so to do an analogous version of this on the comic, you would have to have multiple duplicates of your project, just with some label that distinguishes this version from the previous version. And in each of these, a lot of the files are going to be the same, just you'll have a small change that makes one version be different from previous versions. And this gets really, really cumbersome to keep track of. And I've used that system before. It doesn't work too well. For example, if you need to try something out, you have some small change you want to make, you have to make a whole new version, copy all of you could have dozens of code files and everything. It gets messy. What about comparing the history of changes to see exactly what changed from version 3 to version 4? That gets really difficult to do. And goodness forbid you get to version 7 and you realize, actually, I liked version 4 better. This framework doesn't allow you to easily roll back and say, I want to actually go back. So those and more are all examples of reasons why you might want to use a version control system. So keep that in mind. As far as version control systems go, why GitHub in particular? GitHub is not actually the version control. Version control happens under a program called Git. But interacting with Git by itself, you have to use what's called the Unix command line. Some of you may be familiar with that. I'm only very vaguely familiar with it. It would be a major impediment to my work if I had to use Git through the command line. And so what's been developed is this very comparatively user-friendly interface of GitHub. So GitHub is something that lives mostly online. It's a website. You can go to github.com. It offers all of the version control benefits of Git, but it also is kind of this GUI, this graphical user interface, where you can also have a desktop version. So I'll talk a little bit about the details of how this works, but you have a desktop version where you interact with your files locally, and there will be an online version, which sort of is the centralized version. Online hosting, you can host and share all of your code and data files. You don't have to email to collaborators files back and forth. They know exactly where to go to find the most current versions of all your files. Along those lines, definitely facilitates collaborative development. There's features for project management, project documentation. There's free and pro versions. In general, you're not going to need to pay for GitHub. I've not seen a need for that. So, and I should mention too that GitHub isn't the only software that offers these advantages. There's also something called GitLab. There's others out there that do similar things. I've found that GitHub seems to be the most popular though. So yeah, if you're tired of sending code and data files back and forth with a collaborator, changing file names, identifying which lines you changed. Oh, I deleted this, I added this. Welcome to GitHub. So here's one example. You see a list of the history of changes that have been made. These are called commits. We'll talk about what that means here in a little bit. But if you were to zoom in and click on one of these, for example, it would take you to something that looks like this. And this is a file diff. So this shows exactly what lines changed from some original version to the changed version. So you can see I deleted these 3 lines, replaced it with this line, and this line here was changed as well. If I was comparing these 2 files side by side, I probably would not identify what changed here on line 99. It was just the deletion of this 1 comma was all that changed. So that can very easily and quickly show you changes in file versions. So that's a big advantage. File diffs built right into the GitHub interfaces. So as far as getting started, types of things that you'll need, obviously you'll have to make a GitHub account. It's free to do. Also, you'll want to install GitHub Desktop. So that's a desktop application that you have on your computer. Interact with your files locally. In general, you want to have some kind of a beginner's knowledge of Markdown syntax. If you're not familiar with that, you can click on some of these links in the slides that'll be shared afterwards. But that becomes really useful to document things. And then a working knowledge of terminology. And there's a whole lot of terminology, and I'll go through some of the key players in these slides. So first off is what's called a repository. I might abbreviate that and call it a repo, but it's basically a folder. It's a directory with files that are under version control. So Git is going to be tracking the files that are within this repository. If something's changed in those files, it's going to keep track of that. And then as far as repositories go, you'll have a local copy. That's something that's found on your hard drive. And then you'll have what's called the remote repository. And that's the version that's found online. And so much of the work that you're going to be doing will be done locally on your own computer. You'll document those changes, say, I want to keep these changes, then you'll add them to the remote repository. So say that there's a repository that exists remotely already, but you don't have a local copy of it. Say a collaborator has been doing some work, they want to bring you in on it. Cloning means take a remote repository, make a local copy on your computer, and now you can interact with it and push stuff to the remote repository. That's only something that you need to do once per repository. Commit. So this is a small set of changes that you're making on your repository. They all kind of accomplish what we might call an atomic task, just a small incremental change that's going to accomplish some larger goal. And each time you make a commit can be, I changed this line of code. A commit could be, I added a space in between these 2 letters. It can be as small or as large as needed to accomplish this atomic task. But each time you make one of those commits, you'll get a chance and you'll have to write a little message that says, what does this change do? What does it accomplish? And this is a little comment that goes that they're getting impatient with writing GitHub commits, and that says that they get less informative as time goes on. So you can just see that don't do this, right? This is not what you want to do. You want to be informative with each of your commit messages as time goes on. Fetching, that's something where we would say, I have a local version of the repository. I want to see if it's up to date. I want to see if it's all perfectly synced with the remote repository. That's just a little button you'll click that says, check to see if we're up to date. Pulling and pushing. If there's a change that exists on the remote repository but not on your local repository, pulling will bring that change down to your local repository. The opposite of that is if a change exists on your local but not on the remote, pushing says, let's push that up to the remote repository. Let's push that change I made locally so that other collaborators can have it. A branch. So this is one of the key aspects of GitHub that I've found to be most useful. So you can make an isolated version of the repository. Any changes you make on that branch don't affect other branches. So this is similar to copying the whole folder over again and making changes in that other folder. But in using the Git framework, you don't have to make that copy. You just say, let's start a new branch. And at any time, you can switch back to your other branch. And the files are still all there just as they were before. So that's the notion of branching. As far as branches go, you'll have a main branch that stores sort of what we would consider the best version. If you were to share your project at any given time, this is the version that is most reliable. So just to sort of help visualize some of this, this is what's called a Git graph. Helps you visualize the development history. Progress in the project is going downwards on this image. A commit is visualized by each of the dots here on this line. That means you're making progress on your project. And so this is just one line going down is one branch. You see some examples. You're initializing the repo. You might add some data files. That's a commit. You make another commit and say, I'm going to add some code that does something with the data. Another commit would be add some basic models or something. Just simple examples here. So that's your main branch. And you decide, okay, I like everything that's on main right now, but I want to try something out that I'm not sure if I'm going to like this or not. I don't know if I'm going to keep it. Let's create a branch and say, so that the main remains untouched, let's try something new. And so that's what a feature branch might be. So main remains untouched. Let's go and so update some models. Let's add some new variables, create some new plots, for example. And then if ultimately you decide that you like those commits that you made on that feature branch, you can merge them in with the main branch. So that's what a merge means, is it would look something like this. You'd say, okay, they don't currently exist on main yet, but I'm going to merge them in, and now the feature branch and main branch are up to date. They contain everything of the same. And so now after this merge, you would want to go and delete that feature branch. It doesn't have anything on it that is not on your main branch. So that's, and if ultimately you decided I didn't like the changes I made on feature branch, you could chop that off and say, delete this whole branch. Those commits are garbage. I never want to see them again. And then you're just back to right where you started with main. A terminology that's kind of specific to GitHub is what's called a pull request. That just, especially if you're working collaboratively, you'll say, okay, I have a branch. I want to merge it in with main. What does everybody think? And so you can write some documentation about what you changed, why, and it's basically just performing a merge in a documented fashion. So you can do merges without pull requests, but it's nice to do, especially if you're working collaboratively. Okay, so here I've got some miscellaneous topics that are sort of just bonuses. So I actually went through that material relatively quickly. We'll be able to revisit any of it with the specific question and answer time period. But so one of these is what's called the issue tracker. So you have one of these per repository, and this is a place where you can sort of create, you can sort of think of them as comment threads. So if you click on each one of these, that would take you to like a comment thread section where you can post stuff about, hey, I'm facing this problem right now. You can put in screenshots, put in code. It uses Markdown syntax. So this is where one of those places where if you're typing out stuff, it's useful to know something about Markdown. I use it as something of a research notebook. Document what worked, what didn't work, what was the ultimate solution to this problem I was facing. You can use this numbering system, which helps link issues together. You can reference specific commits that say, this commit helped address this particular issue. and they're comment threads. So a collaborator can go in and post a comment and say, here's my idea for how you might solve that problem. You can tag people, say, hey, I don't want to mess with this. It's on your plate now. You can group them. You can tag it, add these labels to issues. Here I've got some showing where I think it's a low priority issue versus something that's high priority. Open versus closed. Open means this is something that hasn't been resolved yet, and they're kept separately from your closed issues that, once you've gone through and solved everything, you would mark it as closed and say, okay, I don't need to really consider that part anymore. So that's the issue tracker. I found it to be really, really useful for help to keep track of things. Git ignore. This is a really big and important topic that takes a little while to get used to, but in your repository, there's going to probably be some files that you don't want to commit when they change. So some examples are, a big R data object. If I make some changes to that, I don't necessarily want that to have to commit that change. Some cases I might, but in general, often not. I use R Markdown a lot. A lot of these, sort of intermediate files get created. Output files get created. I don't necessarily want to have to commit it each time a change is made to there, because it can be reproduced at any time from the source code that I am committing to. So in general, I don't want to track changes on those files. So this is just a file that you put in your repository. It's a hidden file. It starts with this dot. And it just says anything that matches these types of patterns, ignore them. They'll remain in your repository. You can make changes to them, but you'll never have the opportunity to commit those changes. And anytime you push to a remote, those files won't be pushed either. This is a really useful feature I use. I just create a scratch directory in my repo and say anything I put in that file in that folder, don't worry about committing it. So you can use that kind of syntax. So yeah, git ignore gets to be pretty important. Merge conflicts, another pretty big topic that I just want to touch on briefly. I consider this when things go wrong. So if you're trying to merge two branches that are inconsistent with each other, you're going to run into problems. So here's a Git graph. You have your main branch, you have a feature branch. You made your feature back here and you added some commits to that feature, but then either you or somebody else went in on the main branch and added some new commits. So these commits don't exist on the feature branch yet. And so if you go to try to merge this feature in with main, say they changed some of the same files that you changed in your feature, when you go to merge, Git is not going to be able to figure out what version to keep of that. And so that's where a merge conflict will arise. They can be avoided using a couple steps or a couple just sort of tenets. In general, if you're using a branching workflow, you don't really want to be committing to main. Really just commit to your feature branches. Once you like those changes, merge them in with main. If you're working collaboratively, I like to use this framework of one branch is one person. That really minimizes the amount of conflicting that can happen. Otherwise, if you are working collaboratively on a single branch, make sure you're communicating with that person and pulling frequently. That'll help make sure that your branch is the same version as their branch. Rebase, that's kind of a complex topic. I don't want to get into it too much here, but just if this is a tool that can be used to say, instead of starting this branch back here, let's rebase it and start it up here. And so that these commits will now exist on the feature branch. More details at all of these links you can click on. If you're faced with one of these merge conflicts, GitHub will tell you about it and you'll get a chance to resolve it. You'll have to go through and select line by line. These are the two lines that are conflicting in this file. Which one of them do you want to keep when you go to do the merge? And so that's how it gets resolved. generally it's better to try to avoid them from happening than to go back and try to fix the problem. So these are the types of things you can do to avoid it. R packages, this is a major advantage that I've found. If you have an R package on your computer that you work on and you want to share it with someone without having to post it to Graeme and without having to send them a compiled package of the compiled source files, you can host that repository on GitHub. And then users, if somebody wants to use your package, they can just go and install it on their computer using these two lines. They need a package called remotes, and then this line of code will say, go from this GitHub user and this repository name, which will be their package name, just install it. So this book by Hadley Wickham has got lots of details about how to write our packages, and I believe there's a chapter about sharing how to use this GitHub framework for sharing your packages. And that's something I found to be really useful. Another thing that gets to be really useful is you've got some code and say it's as part of a journal, a manuscript submission. Increasingly, journals want you to share your code, share your data, which I think is a really good thing. How do you do that, though? Do you just want to upload a zip file that has your whole project? You could do that. GitHub includes this collaboration with something called Zenodo, though, where you can tie them together and say, this version of the repository is the final version that was used to create the figures or the plots, all the output that's shown in the manuscript. This is the manuscript version, and I'm going to archive it, and you'll get a digital object identifier for that version. And so that when somebody clicks on that, they'll say that'll take them to the exact version that you want to share. And if you've been using GitHub all along, it'll also show the development history. They'll be able to see the work you did to get to that point. So there's some steps. It's really pretty straightforward to do this. Makes it pretty easy. So not going to step through it line by line, but you get the idea. You'll have to make a Zenodo account and you tie them together, and then you start tracking that GitHub repository on Zenodo. So I think this is my last slide. Practice makes perfect with these things, but it's important to not be too perfect. This is something I've run into, that time you spend documenting changes in GitHub is time you're not spending making more changes, which those are actually what progresses your work forward. So, spend time with this stuff, but don't be too much of a perfectionist with it. Definitely strongly, especially for beginners, start with something of a toy analysis. Don't start off with some, important real analysis. Especially working collaboratively, get the feel for how this works on just a toy problem. And see, there's going to be an upcoming webinar from PNAP that I'm going to give that's going to be more of a sort of how-to tutorial. I haven't worked out the kinks on it yet, but it'll be sort of more interactive. I'll give an example of what it's like to actually interact with GitHub as part of working on a data analysis project. So I think as the last slide, I'm just going to pull this back up again. I think maybe this could be useful for Q&A. Any of these topics maybe that were complicated or I didn't explain very well. So yeah, that's all I've got.
Perfect. Right on time too. Excellent.
Great.
All right, we're going to open. Thanks, Ben. That was really great. We're going to open the floor for comments. I see that Gabriel's typed a comment in the chat. I know you can see them too, Ben, but I'll just read them in case anybody doesn't have their chat open. Gabriel has run, so I have to run, so I'll probably miss the response in Q&A, but go back to the recording. Can I use GitHub in a non-collaborative manner, simply to work on a living document that will have changes over time, so I can track versions while eliminating the version issues you described earlier?
Absolutely. Yep. So, and you don't even need to use GitHub Online. If you want to do just locally, GitHub desktop, and that'll allow you to do this stuff. You don't even have to ever push it to a remote repository. So yeah, you can definitely do this all on your own.
Excellent. Anyone else? Feel free to unmute yourself, raise your hand and unmute yourself, type words in the chat, and also we'll swing back at the end. Or Ben, I'm assuming people can reach out to you if they have questions.
Absolutely.
All right, cool. Brian Mashoff, I saw your hand go up first.
Can you hear me?
Yep.
Just wanted to follow up on that for people that just want to use it by themselves. It's I read somewhere somebody came up with this idea that you're actually think of yourself developing with your past self, because a lot of times, you'll have a project and you have to get back into it months or years later or whatever, and you have no idea what you did, and how you did something. And this allows you to go back in and see, basically look at the steps that you made along the way. So it is both for data and for everything. It's a way to sort of enforce that, documenting it so you can figure it out later, because that's a really big time sink if you have to go back in. So it's not just for, collaborative other people.
Excellent point, Brian. I've used it that way a whole lot to be able to changes I made, and that'll bring me right back into this project without having to keep that in my head for months. Yep, really useful.
Awesome. Thanks, Brian. Dan Brown, I see you out there.
Well, hello. Hey, Ben, thanks for the presentation. I really appreciate that. And I wanted to ask, is there a way to automate pulling and pushing to the remote repository? We use GitHub somewhat, but not everybody uses it all the time, and it's really easy to forget to push your commits to the remote repository. So is there a way to do that so that we don't have commits sitting on somebody's computer and then I don't have them?
Absolutely. Thanks. Yep. Yeah, great question. I haven't dabbled too much with this yet. I have it on very simple projects, but there's something called GitHub Actions, which is automation. So you can give it some rules that say, these are the circumstances that when this is triggered, I want you to take this action. And that action could be, I think you could probably say push all changes from this user up to the remote. I haven't used it in that specific context, but you can use it to say, re-render that. This is how I've used it, is re-render this R Markdown document with at this periodicity. Every week, I want you to rerun this R Markdown document and commit those changes that were made. And I don't have to go in there and do it manually every week now. That's something that just gets handled automatically. So there's a lot of different examples you can use with GitHub Actions. It's not the most straightforward when you first start with it, but there's a lot of details out there on how to use it.
Yep. All right. Great. Thanks, Ben. Appreciate it.
Thanks, Dan. All right. Christopher Johnson has a question. Are there privacy concerns with creating projects using the platform, such as contracted data and analysis being uploaded to a third party?
Yep. So in general, I should have mentioned this. At any time, you can say, I want my code to be private, and you have the option to make it a private repository where only you and collaborators can see it, and then you can make it public at any time too, where then the whole web gets to see it. So in general, I try to keep my stuff private while it's under development. I don't want other people to go in and use that code or to see it because it's ugly. It's not in shareable form yet. But then when I'm done with it, I'll make it public. So that's one aspect that can help prevent that issue. If I'm working with someone else's data that is, collected by some other agency, always important to get permissions to publish it on your GitHub repository. They might say, no, I'd rather users go to our in-house, database to get the data files. That way we don't have multiple copies of these data files out there on the web. So those are some issues I've ran into in the past. But in general, that's something you'll have to navigate is just getting permissions to share this stuff.
Yeah, that's a great question. All right. Anybody else? Kind of give it a pause here for a moment. All right, I don't see anybody typing. Okay, excellent. Fantastic presentation, Ben. That was super helpful. I think a lot of people are using Git, and it's really kind of on a lot of people's radar. So that was super helpful, and I appreciated that overview.
Great, thanks, Megan.
And before we move along, I'm going to give a shameless plug for PNAMP Fish Farming Workgroup. As Ben mentioned, today's presentation was kind of an overview of GitHub. And at the FMWG Pit Tag Analysis webinar series, he's going to do a deeper dive into GitHub. That series is currently under development. I'm meeting with the presenters next week, so I should have more details soon. If you guys would like to be added to the listserv for that project, Amy's going to drop my email in the chat. So just let me know and I'll get you on that list so you can kind of be up to date on that. And next up, we have Graeme Diack. As with Ben, I'll give you background on Graeme and then I'll hand it over to him for his presentation on our Shiny. Graeme is a data specialist with the Atlantic Salmon Trust and Missing Salmon Alliance in the United Kingdom. Following a decade of working in IT infrastructure, he's reskilled to data management by completing a master's in mathematics and data analysis over 2018 and 2019. Since his graduation, he has been with the Missing Salmon Alliance through the Atlantic Salmon Trust to develop data solutions for the Likely Suspects Framework project. His role as a data specialist is to lead on the discovery and mobilization of databases of biological records and environmental parameters in the support of this project. More recently, he has taken on a data stewardship role directly with the Atlantic Salmon Trust, allowing him to put into practice biological research data management. And with that, go ahead, Graeme.
Thank you very much, Meg. Yeah, I apologize as well. That was a bit of a mouthful for you. And yeah, there's lots of acronyms involved in my work, that's for sure. Is it okay if I share my own screen for this presentation, because I have added one more slide?
Oh yeah, absolutely.
Okay
yeah, completely. No, totally.
Thank you. So I'm going to share. When it's loaded, is that visible to everybody?
Yeah, looks great.
Good.
Cool. So thank you very much for inviting me along to this. So as Meg introduced me, my name's Graeme Diack from the UK, and I'm here to present a little bit on utilising R Shiny within our project. So kind of similar to Ben's presentation on GitHub, I'm kind of going to do the same thing, but for R Shiny. So we've been I've been working with the trust now for almost 5 years. This is a team that I'm working with, and the Likely Suspects framework is the kind of main project that we have been working on within the Missing Salmon Alliance. They do have other projects on the go in the Missing Salmon Alliance of 5 organisations in the UK, with the Atlantic Salmon Trust being one of them, which I am an employee of. And here's my team here. Colin and John, the 2 chaps, are possibly going to make it today, but I think they weren't able to come along. But our team consists of biologists and mathematicians. We have one PhD candidate, Ashlyn, and we have some consultants as well. And we're a mixture of the Atlantic Salmon Trust and Strathclyde University. So the Likely Suspects framework, it's basically the flagship flagship project of the MSA, and it aims to provide vital knowledge on the drivers of salmon mortality from across their life cycle. The project involves multiple work packages, building knowledge and tools to achieve this goal and inform ecosystem-based approaches to salmon conservation and recovery. The work packages are here, and essentially we have basically the first task we decided to tackle was basically finding out what data is out there and available for Atlantic salmon. And there was an ICES workshop in 2019, which developed a very, very long report on data availability that is of relevance to Atlantic salmon. And as you can imagine, it was very across lots of different disciplines. So oceanography is a large part of it, as well as biology, freshwater, ecology, and this document came out, and it was extremely long and quite difficult to really absorb what the message was. So we began to develop, our work package one was to begin to develop a data library. So essentially we digitized that document into a web application, which was built in R/Shiny. And we then, once we had kind of started that and got the ball rolling with that data library, we brought in our mathematicians and modelers from Strathclyde University to start building a mortality framework. Now, I'm not a mathematician or a modeler, but I'll go through the model a little bit just to as much as I can to give you a summary of how that works. And whilst we were building that model, the goal was also to make it so that it was accessible and usable, because there are many similar models out there that are used within working groups or within projects, but reuse of the model itself tends to be a bit more difficult because they are complicated to start up, complicated to understand. So they tend to be all within their own kind of silos. So we wanted to build a model that was simpler than these models. It's actually it's not a stochastic model we have. It's very quick to run, but it takes in lots of different mortalities across the Atlantic salmon's life cycle. But the advantage of it being quick to run means that we could think about actually producing some kind of accessible form for this model so that people would be able to actually use it directly. And that's what Work Package 3 is based upon. And Work Package 3 is actually what the focus of this presentation is about. And I will go a little bit into other R/Shiny tools that we've produced as well, but the main one that we've been working on for a few years is our decision support tool. And work packages 4 and 5 are currently the work package 4 where we've started working on, where we're focusing on changing or rebasing the model so that it can be used across a wider selection of catchments. And work package 5 will be probably following quite soon after that. I imagine we'll be starting that this year. So the model itself, it started life as a MATLAB model, but essentially it breaks down it takes this idea of the life cycle being broken down into domains, and each of those domains, the transition from one domain to another in the life cycle of the salmon has a loss or a mortality. Some of these mortalities are quite well understood. For example, the mortality from the juvenile salmon leaving the river, going out to the ocean to feed and then coming back and returning as an adult, we have quite a good understanding of the actual percentage of adults that are returning, and it's something like 3% at the moment. So we basically were able to estimate the losses across these, a more granular domain structure, not just freshwater and marine, but as the transition from eggs to par through to smolt. We were able to estimate the losses based on some data that was available in some of the rivers around the UK, and build a model that ran but from a set number of beginning eggs, and produced a set number of adults, at the end of the one cycle. So as we were developing this, we thought about all the different aspects of how should we, the life stage, the life histories of the animals. So the juveniles will stay in the river for 1 year, some will stay for years, and then anything in between. And the adults are the same. Some will go to sea and come back again after 1 year, or some will go to sea and come back again after 2 or 3 years. But we had to keep it as simple as possible. So future work will expand upon those life histories, but at the moment the model only really tackles one of those choices at a time. So we can set it to tackle, say, 2-year-old juvenile and a 1 year sea winter adult, we call them, where it goes out to sea for 1 year. And so these losses essentially form the backbone of how we present this to a user to be able to interact with this model and to use the model in some kind of decision support system. They are able to manipulate some of these losses. So whilst we were developing the model, the River Bush in Northern Ireland was our index river of choice. It had basically the data available to construct all these mortalities and make quite a reasonable estimate of each of the mortalities between each stage. So the model was built, and then it was tuned to the real data from the River Bush. So we have as listed there, the lengths of adults and juveniles, marine return rates, the proportions of smolt and sea edges, along with the accessible wetted area. So our base model is based on that. So whenever we run it, it's all the numbers that come out are essentially the numbers you would expect to see on the River Bush. So onto the work package 3, and the kind of main piece of this presentation was how to improve accessibility to the model that we had. We knew that we wanted to use R-Shiny because we had used it before. We also did think about looking at technologies such as going through Python, but in the team we already had the R skill set, so we stuck with that. But here are some of the things that we felt were important. So a public web application is an excellent way to push this model into the kind of into the public in an open way, and then designing an intuitive user interface is a key aspect of it. We wanted to have some kind of form of persistent storage so that our users would be able to build up a suite of different model runs. And then also we wanted to create some kind of formal structure where the users would be able to visualize and report on the outputs that the model was producing. So just to kind of give you a taste of what R Shiny actually is, essentially the R programming language on the left here is, I'm not sure if many of you are probably familiar with it. It's very popular in the biological sciences, and it's classically a statistical software package, but there has been a library developed for it called Shiny, which essentially allows somebody with R programming experience to quite easily, once you kind of get over some of the concepts, once you understand some of the concepts behind web applications, to quite easily create dashboards for data and online presentations for data, and you can publish them online, or you can share them via Markdown document, things like that. So this is the kind of base example that R gives you if you were to start your R Studio and ask for a R Shiny application. You'll get this one. Essentially, what it gives the user is a sample data set, the old faithful geyser data, and it gives you a slider that you can control the histogram on the right. Control the bin sizes of the histogram. So quite kind of basic and easy to start. And the great thing about the R Shiny ecosystem is that there are hundreds and thousands of users online who put examples up. So there's an R Shiny gallery online, and you can go straight into those and basically, borrow ideas from there and start building these kind of dashboards very quickly with your own data. However, we have taken it to probably, maybe not to the limit, but we've certainly kind of pushed our R Shiny web applications to a kind of stage where it's more than just a dashboard. We're creating kind of a almost full web application. And whether or not this is a good idea or not, I'm not sure. I've got a slide later on to kind of discuss that. We've basically built something that looks like this. I do have a live demo coming up. So this is the model. This is the web application with the model running behind it. And we've broken it down into the users are able to select from a list of catchments, which are taken from kind of government data sets. They're able to view the data on those catchments that are, for example, the conservation regulation assessments. So the yearly assessments that come out, they're able to view the data here, and we pull that from other online sources, some of which are actually R Shiny web applications themselves. We're able to pull in some kind of general context information. So when a user is looking to use the model for their own catchment or watershed, they're able to see some of the challenges that already exist in that watershed, some of the wetted areas and things like that. And the way we've built this is that the user is able to select a catchment and build some reference cases using the model based on that catchment. And once they've built some reference cases, the model will give them an idea of the the current situation in their river. So they would maybe tweak the user controls and make the model reflect more of what their river actually looks like just now. And then once they've done that, they can go on to test scenarios on that baseline reference case. And once they have a few scenarios that they've tested, they can actually visualize the results, so compare the baseline and the scenarios. So I'm going to do a live demo, which is always not recommended, but we'll see where this goes. share my window. So give me a shout if this has not loaded or if you're all looking at a blank screen.
Looking good.
Good. So this is the R Shiny app. So as you can see, it's more than just the kind of base dashboard that we created. And so the user journey here is, as I mentioned, you would select a catchment. So say I'm interested in West of Scotland River. Here's one I prepared earlier. Not that one. So River Applecross in the west of Scotland there. It loads the information here, like I was saying, from government assessments, and also from if there's any fishery trust data, then we can find it here. Some figures here that have come from the fishery trust on the life history of the that river. So most of the smolts, most of the juvenile salmon leave the river at 2 years old, and most of them come back after 1 year. And there's some other information here. This is stock recruitment plots for that river that is based on, again, official data from the Scottish Government. So we can see that this river is, I'm not sure if you're, I'm not going to explain a stock recruitment curve because I don't really understand them fully, but essentially the red line is the freshwater density dependent aspect of it. So this is the population maxes out at a maximum density here, and then the blue line is the kind of marine survival, and where they cross is kind of expected to be the kind of equilibrium point for that system, or where that system currently resides, and the ideal place for that point to be is actually kind of over the curve a little bit. And then we can have some environmental data here. Loads. So we have let's click this again actually just to get the no, sorry. So we have some river temperature data here, again coming from official sources. Not in a particularly sophisticated way. I'd like to get this so that it pulls it automatically from through some kind of API, but this is actually just pulled and then turned into a CSV and then is available when you choose that river. And then we have some layers here that you can look at. We have something called the Water Framework Directive over the European Union concept, where people had to basically assess all the catchments across the UK and Europe. So you can have a look at your own catchment. So I think it was up here somewhere, the Applecross one. You can have a look and see how's my river doing. Is it, what status is it? So these are all just to give the user a bit of the stuff that they should probably know already if they're a river manager, but just to give them a bit more an idea of what's going on in their river here, and then a sources page where all this data comes from. But to get into the actual the use of this this tool, so here we have the actual interface with the model itself. So the model is started off in MATLAB, it was then transferred to R so we could run it behind this in Shiny. So we have the parameter controls here on the left, which is essentially a cut down version of the full model parameters, but the ones that are most significant for management actions. So we chose the ones where the managers would possibly be able to have some kind of either influence or it's important to know. For example, they can have influence over these stage-based mortalities, egg loss. They can improve that, or they can reduce that through some management actions, but they might not be able to have any kind of influence over the marine conditions. But it gives them an idea of if marine conditions continue to decline as they have been, what's the impact going to be on our system. Again, this is all based on the River Bush, and we are currently developing it to expand it out to other rivers. that requires a retune of the model. And when the model gets retuned to another river, then we are able to plug that into this same interface. So the user would basically create a reference case for themselves. So let's just save the default reference case with some notes. Save that. Let's dismiss that message. And once you've got a reference case, you can move on to test some scenarios against it. And you can have multiple reference cases. So there's a drop down here. If you've got more than one, you can choose which one you want to play around with. And so we want to test some scenarios. So let's say that marine conditions do decline to poor. So there's some information here that tells us that the model is reflects 2010, so a decade ago, and the best conditions reflect 1980s. So this is again going back to that bush data set that we have, and that kind of conditions, the marine conditions were better then. And so we can say what happens if our marine conditions reduce to poor. So reduce marine conditions to poor. Save that scenario. This will come up, we'll just, because I'm not logged on, it complains at me. So I've got one scenario down here. So I can say, okay, what happens if the marine conditions remain at poor and we do something in the river? So we maybe improve our carrying capacity. So we make the river conditions better in such a way that the carrying capacity will be increased. So say we remove a dam or something like that, would increase the carrying capacity of the river. And we can save that, improve carrying capacity. And so the user just goes through and builds up some of these scenarios. So say the carrying capacity reduces to poor. Just do that. I'll do that. I'm doing what Ben was talking about in his GitHub commit notes, just getting less and less informative as we go on. And say that we want to put that back to reset things to default, put that back to poor, and maybe make this egg loss only 10%. How much of an impact does that have? Not very much. I'm looking for something that will get the thing over the line. Let's say juvenile growth to best. So I've changed a whole bunch of changes there. So I've got now 4 scenarios against this reference case. And I would go to visualize results next to give me an idea of how those scenarios compare. So we have a table here which highlights the changes from the default, and you can change the order of those based on these things here. So if you want to highlight some, so say if you had, for example, 20 different scenarios, you might want to order them in a particular way. So you highlight the scenarios you're interested in, compare them. We have the obligatory heat map going on here, which starts to look quite good when you have lots of scenarios going on, but it basically highlights 4 of the key metrics that we feel that managers would be interested in. So changes across freshwater survival, marine survival, and adults entering the river. We have some nice plots here to show us how the models actually, how those scenarios actually perform. The baseline here being the flat red dots, and the scenarios each being the curves. And we have that in 2 different ways. We have a proportional change and the actual adult numbers here. Again, this is one of those things we have to remember. This is the river bush numbers that we're talking about. And if we retune the model to another river, then these numbers will look quite different. And then we have a table here showing us the changes in carrying capacity. So basically, these are the numbers behind the SR curve. So the user might want to look at that. And then this is where I really do hope this works, because the generate report is a little bit flaky. So a report on all the scenarios. Click on generate report, and then this uses a package, R Markdown package, to create a PDF report. Some role probably required. And yeah, I guess I should mention that we use, obviously within the RShiny ecosystem, there's lots of different packages that are available, and we do use a lot of packages. This main interface is actually built in a package called bslib, and some of the standard packages that are available, we basically dug around to find the ones that were best for us. And that's one of the great things about the ecosystem, was we really didn't have to do much from scratch. So here's the kind of the idea of that kind of basic management level report. It gives you always the same, no matter what you do. It will basically give you all your scenarios, or sorry, up to a maximum of 6 scenarios, and your base case in a report here. So you can create a report and take that to your Rivers Trust or your managers and say, these are the kind of things we need to do to say improve a certain situation, and this is the effect that we would expect from it. And there is a login function, so get that up and running. So when you log in, it loads all the previous reference cases and scenarios that I've done before. So lots of testing being done on this. So I can load this one here, and you'll see that that's the settings that I put in for the case, and I've got a number of scenarios that I've loaded as well. And I can go to the visualize results, and it'll tell me there's an error. I think it's just taking time to refresh. So that's with 10 scenarios there. The heat map's starting to show a bit more action there in some of these scenarios. And the user is also able to download the full data output from this as well. So they basically get that as an R file. So I'm going to go back to the slides. Wait, back to the slide I was at. I'll probably take me back to the first slide. Yeah, first slide. So I think I'm kind of, how am I doing for time? Okay. So
Yeah, you got a couple more minutes, Graeme.
Cool, excellent. So that's basically what we've been using RShiny for, and I find it great to use. But there are pros and cons of this approach. We've obviously discussed getting a consultant in to do these things, and there's the kind of you got to weigh up the pros and cons of the cost. Consultants do cost a lot of money, but they get things done very quickly. Whereas versus myself and the team doing it, it's taken us, we've been working on this probably for about 2.5 years, fairly solid, and learning a lot as we go along. So we've spent money on our own salaries doing that, but we've also been able to be very flexible with it as well, because we are able to decide in a meeting we want to do this, and then the part of the team who develops this goes ahead and does it. So we don't have to have a consultant. We'd need obviously a very strict kind of idea of what they're going to deliver in a certain time. And the skill set is a big issue. I'm quite lucky, and I come from an IT background, so I've been able to tackle a lot of the things like using GitHub, using Linux servers, using Amazon Web Services for storage and databases and things like that. But I think that might not be as, I think that's quite unique with us. But it is worthwhile. I think the one of the key things here is that the tools are really becoming available to do all these things ourselves, and the kind of ecosystem of kind of support and YouTube videos and things like that are available to just show you how to do something and how to get something up and running are really quite amazing. So I've leaned heavily on that kind of stuff as well. So it's possible to really do these kind of projects within even a team of biologists and statisticians who are familiar with R. I think we would be quite well placed to begin these projects. And we've built a couple of other tools in R Shiny. So as I mentioned earlier, the data library is in R Shiny and it's fully open and public. It is actually only a metadata catalog, but it's not a data library. That's kind of mission creep there. We also have a pit tag database as well, which is kind of based on the Ocean Tracking Network and kind of approach to tagging metadata, and we use it as for a specific purpose to allow people to very quickly deposit lists of tag numbers, pit tag numbers that they've deployed in salmon or trout, and for that list to be quite easy to cross-reference any detections with, and that's proved quite successful so far. There's been 4 or 5 salmon that have been detected on that out of about 500,000, but the key aspect there is a lot of them were bycatch, and they wouldn't have been known about otherwise. And so that brings me to the end of my presentation. Thanks very much for listening, and yeah, I'll share these slides as well, and you'll be able to follow the links there to some of those tools. The decision support tool itself is actually still in development, so it's behind a bit of a log on. So unfortunately, you won't be able to browse that, but the data library is available and the pit tag database is available as well. Thank you very much.
Excellent. Thanks, Graeme. That was great. And kudos on a successful live demo. All right, we've got about 5 minutes for questions. If you guys want to type them in the chat or unmute, raise your hand. And then, Graeme, do you care if we send out your email with those notes in case people want to contact you?
Yeah, absolutely. It's totally fine. I think my email is on the slide, and yeah, feel free to contact me.
Okay, excellent. I'll just pause for a minute, see what you guys come up with. All right. And then if we have time at the end, like I said, we'll swing back around and then you guys can ask questions of all the presenters. All right. Let me get myself lined out here and give you guys a little bit more time. Okay. I see you there, Caitlin. Good morning, Caitlin. Go ahead and get set up. And our last speaker today, I'd like to introduce Dr. Caitlin Magel, an estuarian ecologist at the University of Washington's Puget Sound Institute in Tacoma, where she spends most of her time using models and other decision support tools to understand the impacts of management decisions across habitats, species, water quality, and social systems in the Puget Sound. Before joining UW, Caitlin completed her PhD at Oregon State University, go Beavs, studying eelgrass in Oregon and Washington coastal estuaries. She also holds a master's in marine science from the University of North Carolina. And go ahead, Caitlin, the floor is yours.
Great, thank you so much, Meg. As Meg mentioned, I'm going to be talking about work in Puget Sound and how we're using models as decision support tools that help us to compare social and ecological trade-offs between management alternatives. I'm here representing my work. Oops, sorry, let me move some screens. Okay, sorry about that. So I'm here representing my work at the Puget Sound Institute, but we have a lot of partners that are working on this with us. And so just want to acknowledge that there are a lot of people who have contributed to the work that I'm talking about today, from diverse agencies and state and federal agencies in our area. So this will not be a surprise to many of you, but stressors originating from human actions and population growth and climate change threaten the freshwater, nearshore, and marine species and ecosystems, as well as the social and economic systems that depend on them. These impacts can be particularly far-ranging and complex in urbanized coastal areas where long histories of development threaten natural resources that we depend on. A good example of this is Puget Sound. The Puget Sound region in Washington has become highly urbanized around the coastline, as you can see in this map of impervious surface on the right here. And we're now seeing many symptoms of degradation. A major challenge for us is to understand how future conditions of population growth and climate change and our decisions to manage for them will affect the interconnected natural and human systems and minimize trade-offs among multiple regional recovery goals. So the recovery objectives for Puget Sound, or the vital signs, are used to track the health of Puget Sound. Recovery plans establish the indicators of progress and identify specific interventions needed to achieve each objective. But latest status reports indicate that most vital sign indicators show mixed results, no trend, or are getting worse. So it's clear that we need to do more. But with so many possible objectives and interventions, we need tools to help us prioritize our actions in the context of climate change and population growth and understand potential trade-offs among recovery objectives, especially for the human dimensions objectives, for which we have comparatively less information compared to the more biophysical objectives. At the Puget Sound Institute and the University of Washington, we're working with two modeling approaches that we believe can be decision support tools in this Puget Sound recovery context. So the two tools we're working with are a qualitative modeling tool and also a quantitative modeling tool. Because numerical modeling of complex systems is challenging, we started with a fairly simple approach called qualitative network models, or QNMs. QNMs are essentially operationalized conceptual models, and we can run simulations of the network to observe the responses of system components in response to perturbations. I'll show you more on how the qualitative network model works in the next few slides. We're now also working on a more complex quantitative model suite that combines existing numerical models. Both of these approaches derive from the conceptual models and recovery plans that were developed as part of the vital signs framework, and that included input from regional scientists and stakeholders. Both of these modeling approaches are organized around a watershed framework where activities on the land influence the conditions and species in Puget Sound directly or via connections through freshwater rivers and streams. So let's talk a little bit more about this first one, the qualitative network models. Essentially, we reduce a system to the most important components, or nodes, and link them via simplified relationships between those nodes. So these links are either positive or negative, or they can be bidirectional. Qualitative network models allow us to represent feedback loops and indirect effects as well as direct effects. The analysis of a qualitative network model simulates the network thousands of times using randomly selected interaction strengths for each of the links. So 0 to 1 for a positive link, or 0 to -1 for a negative link. And those are randomly selected for each of these many thousands of simulations. We can then perturb one or more of the nodes in the network and observe the positive or negative responses of the other nodes in the network. And due to the variation in interaction strengths across the thousands of simulations, each node will vary in their proportions of positive and negative responses across all of the simulations. I just want to emphasize that these responses are qualitative, so we're saying only that node Y is likely to increase or respond positively or negatively, but not saying the magnitude of the response of the nodes. So here's an example of what the results look like from a perturbation of a simple network containing just 4 nodes. So the number of positive and negative responses across the 10,000 simulations is given by these colored bars. And we characterize the sign consistency of each node based on the percentage of simulations showing a positive or negative response. So equivocal nodes such as Z have nearly equal numbers of positive and negative responses, something like 40 to 60%. That's kind of in the shaded out bar there, vertical bar. Equivocal nodes, weak nodes have greater than 60% of the responses that are either positive or negative. And then strong nodes have greater than 80% negative or positive responses. So again, qualitative network models can't tell us that a given node increased by X%, but rather that the impact of that perturbation on a node is likely to be positive or likely to be negative. So this is the qualitative network model that we developed for a hypothetical Puget Sound watershed. It included a subset of the biophysical and human well-being vital signs. Those are the recovery objectives identified by the state of Washington and the Puget Sound Partnership. And they're connected to each other in this qualitative network model by human development drivers and other physical, chemical, and biological components of the system. Since there are likely to be some fisheries people in this audience, I'll point out that we have salmon represented across multiple life stages, important forage fish, herring, predators on salmon such as pinnipeds and orcas, and a critical nearshore nursery habitat eelgrass represented in the model among the 32 system components here. This is a fairly complex qualitative network model. You can also make these to be much, much more simple depending on the kind of definition of your system or the problem that you're trying to evaluate using the qualitative network model. In our case, we used this qualitative network model to evaluate scenarios of population growth using alternative network structures that originate from the rural new development and urban redevelopment nodes at the top outlined in red. With projected population growth for the Puget Sound region, development is going to happen in one place or another, but we can alter the nature of how that development proceeds. So in the alternative networks, we varied the nature of the red dashed links originating from these two nodes to represent different proposed development interventions. We compared rural versus urban development scenarios separately and in combination where development occurs on both places simultaneously. In the interest of time, I'm just going to highlight a few of the results, but I also have a link to our publication at the end if you want to see more how we evaluated these different scenarios. So first, we compared rural development only to urban development only. And I'm just showing simplified networks where I'm showing you the nature of the red dashed links from those development nodes. The rest of the nodes and links in the model remained constant across these scenarios. Starting with the rural new development scenario on top, this described a status quo situation where new development on rural land negatively impacts the extent or function of critical habitats and increases runoff from terrestrial landscapes, and also increases the development of transportation corridors, such as the addition of new roadways. In the urban redevelopment scenario on the bottom, status quo redevelopment enacts stricter regulations for stormwater management, but increases wastewater associated with a higher population. In both scenarios, we simultaneously perturbed both of the development nodes, so one positively and one negatively, and then categorized the response of ecosystem stressor and recovery nodes across the many simulations of the model. For stressors, the preferred outcome was a negative or decreasing response, and for objectives, the preferred outcome was a positive or increasing response. So what we found is that in the rural growth scenario, we had weakly positive outcomes for stressors and negative outcomes for most of the recovery objectives. This is an unfavorable outcome. The urban redevelopment scenario, however, had weakly negative outcomes for stressors and positive outcomes for most of the recovery objectives. This is a more favorable outcome. We found that responses were mostly synergistic across the recovery objectives in the two scenarios, meaning that most of them responded positively or most of them responded negatively. But we did see some trade-offs. For two culturally and ecologically important fish species, for example, that being herring and Chinook salmon, responses were either unclear or converse to each other. This makes sense because juvenile Chinook salmon eat herring, but it indicates a potential trade-off that would benefit from further investigation. We also ran some perhaps more realistic scenarios where development happens on both urban and rural lands, and where we might coordinate recovery actions across the landscape. So the status quo scenario here uses the same relationships as before. And then the second network, the bottom one, represented a moderate level of intervention associated with both urban and rural development. So we still have development of new transportation corridors on rural lands, but the extent and function of habitats is restored through recovery actions, and runoff doesn't change using management interventions. And then both urban runoff and wastewater are reduced by redevelopment. So we're enacting stricter regulations of both in this case. Here we positively perturbed both of the nodes, and then again categorized the response of recovery objectives and ecosystem stressors. Stressors typically increased in the status quo, resulting in equivocal responses of most of the recovery objectives. That meaning sometimes the nodes were responding positively and sometimes the nodes were responding negatively. This mirrors our understanding of current ecosystem recovery progress. or really the lack thereof, as measured by the vital sign indicators, which I mentioned earlier. Under the moderate level of intervention, both rural and urban lands, interventions on both rural and urban lands, stressors strongly decreased for the most part, and recovery objectives showed primarily strong positive responses. So that being a much more favorable outcome. So that's just a quick look at some of the results that we get from this type of modeling. Overall, what we found with our models was that it's important where we develop. Urban redevelopment resulted in better outcomes compared to rural development under the status quo relationships. But it's also perhaps equally important how we develop. So we found that on rural lands, increasing the quality and extent of critical habitats such as floodplains and riparian areas was impactful. In addition, limiting the development of new transportation infrastructure reduced the impact of new stressors from roads like toxics. And both actions had local and downstream benefits. Urban redevelopment presents an opportunity to address legacy issues, which we believe can contribute to environmental justice. Green infrastructure in urban lands provided the potential to maximize outcomes for both people and the environment. And then we also found that coordination of urban and rural interventions resulted in better outcomes compared to either intervention applied separately, indicating that this cross-watershed or cross-jurisdictional coordination results in efficiencies that could help to achieve those large-scale objectives. These qualitative network models are useful for evaluating these kind of high-level trade-offs, but the next logical questions are always, okay, so where and how much? How much intervention do we need? Where do we need to put it to achieve our stated objectives? For that, we need complex mathematical and spatially explicit models. So this is where our quantitative model comes in, that being the what we call the Puget Sound integrated modeling framework, which we hope is going to allow us to answer the where and how much questions. We benefit in Puget Sound from having several well-developed and tested quantitative models that can be used in concert with one another to address these pressing management questions. So our modeling teams are working right now to link these models together, essentially getting them to talk to one another. One model hands off results to the next model. This has been a technical and Herculean task to create a suite of complex quantitative models that will cover the entire Puget Sound watershed from mountains to the Sound. So what does this kind of data handoff look like, and what are the models involved? The first model in our chain is called the Land Cover Change Model, which was developed at the Puget Sound Institute. It uses statistical modeling to derive past land cover trends and then projects them forward into the future. So tracking changes in broad land cover classes. That model can then hand off information about future land cover to our watershed eco-hydrological model called VELMA. This model is developed by US EPA ORD lab in Corvallis, Oregon. This model is an eco-hydrological model, like I mentioned, so models hydrology and the fate and transport of nutrients and toxics and water flow across the landscape. So this model is being parameterized for all of the watersheds in Puget Sound, and then we'll hand off information about freshwater flow, nutrient loads, and toxic loads to our estuarine circulation and biogeochemistry model called the Salish Sea model, which is developed at the Pacific Northwest National Labs. This model circulates and transforms, calculates primary production in the Salish Sea, including Puget Sound, and then can hand off information about nutrients, toxics, temperature, dissolved oxygen, etc., to our food web model called Atlantis. This is a marine end-to-end food web model that includes information about biomass, abundance, toxics accumulations in fish, and includes information about fisheries harvest. We also are pursuing integration with a freshwater salmon habitat model. Perhaps some of you are familiar with the HARP model. And this is a salmon life cycle and habitat model that will allow us to capture the influence of freshwater habitat features and changes, including in-stream temperatures, floodplain connectivity, migration barriers, etc., on salmon spawning and productivity and capacity metrics for each of the freshwater rivers and streams based on individual salmon populations in Puget Sound. We can then extract those salmon productivity and capacity metrics from the HARP model and essentially tune the spawner-recruit relationship in the Atlantis food web model. The HARP model is only available for 2 watersheds in Puget Sound, the Snohomish and the Stillaguamish. So we'll kind of have to extrapolate those results to other watersheds in Puget Sound. But this allows us at least to say something about changes in freshwater habitat and impacts on salmon populations in Puget Sound. And then, of course, we recognize that this is a social ecological system. So humans kind of are at the center, both receiving impacts from the biophysical models and putting additional pressures or benefits even to the biophysical landscape. So we're pursuing now what a human systems model looks like as kind of the central feature of our integrated modeling framework. And each of the biophysical models can tell us important human dimensions, aspects like information about forestry or drought or wildfire risk, water quality, fisheries harvest, housing density and land conversion, etc. So with the models now linked, that being said, that the data is handed off from one model to the next, we are posed to ask large-scale ecosystem questions about where and how much intervention we need to mitigate the effects of ongoing population growth and climate change and other anticipated stressors, and ultimately how we move towards Puget Sound recovery. So we're working with stakeholders now to decide which management scenarios to pursue first. We received the most support to design model runs, at least initial model runs, that ask questions about riparian management and stormwater infrastructure. So we're still refining exactly what these look like, but exploring ideas of scenarios around riparian buffer widths or lengths, the placement of riparian buffers, such as maintaining or extending buffers on the sunny sides of streams to increase shading and hopefully reduce stream temperature. And then also floodplain connectivity, either restoring or increasing floodplain connectivity. And then for stormwater infrastructure, we're exploring the idea of evaluating scenarios where we improve existing infrastructure or implement new green infrastructure or low impact designs and see what kind of influence that can have on downstream impacts on the marine food web and marine conditions and the human system. I think I have a few minutes left, so I'm just going to kind of quickly at a high level compare and contrast these two decision support modeling tools. So the qualitative network model and the integrated quantitative model suite. So qualitative models allow us to compare relative outcomes. They provide strategic advice, and they allow us to integrate kind of non-quantifiable elements, in particular the human dimensions, where we might not fully understand the mathematical relationship between salmon and human well-being, but we know that that relationship exists, and we can include it in a qualitative sense. These models are also rapid and iterative, so you can run a bunch of simulations fairly quickly and evaluate those kind of high-level relative outcomes. The quantitative model suite is going to allow us to evaluate response magnitudes. So, how much more salmon do we get? By how much does water quality improve? And this will provide kind of tactical advice, the where and how much questions that I talked about earlier. But they are much more computationally and time intensive. So it's going to take us several months to do a complete model run from the land cover change model to the Atlantis Food Web model. It's also involving a huge team of people to be able to do that. So much different as far as kind of the time and computational capacity required. But both of these decision support models allow us to test assumptions, identify uncertainties, and evaluate trade-offs across the social ecological system. And really, by combining both the qualitative and the quantitative approaches, we are able to synthesize decades of terrestrial, freshwater, and marine information. Some of that is quantitative data, but also qualitative information or assumptions about the system, and can allow us to understand the cumulative and interactive effects of multiple threats to Puget Sound. And then hopefully allow us to identify comprehensive solutions across those social and ecological objectives. So these models have strengths and weaknesses, and really by using both of them, we can probably achieve better answers, better decision support. So thank you all very much, and thanks for the invitation to present in this session. I really appreciate it. If you want to learn more about the qualitative network model project, again, this QR code will take you to our publication in Frontiers in Marine Science. And then if you want to learn more about the quantitative integrated model suite, the second QR code will take you to our project webpage. Thanks very much.
Excellent presentation. Thank you, Caitlin. All right, I'm watching the chat, and if anybody has any questions, feel free to unmute, ask away. All right, and then we'll open the floor too if you guys have questions for Ben or Graeme. Don't be shy. And Caitlin, I'm assuming it's fine to send out your email as well.
Yep, definitely. Please reach out to me if you'd like to learn more or have questions about either of these approaches.
I have a question. This is Jen Bayer with USGS.
Yeah, go ahead.
And I missed the start of the presentation. I am so sorry. So I apologize if you covered this, but some of us are working on improving data mobilization and access for the amazing, complicated work that you are sharing with us today. Do you have any wishes for how your work might have been more efficient if data were available in different ways, or just your general thoughts about that might help us inspire us on the data mobilization side of this work.
Yeah, yeah, that's such a great question. So the qualitative network model approach really benefited from these recovery plans that the Puget Sound Partnership and their partners developed. And specifically, there were conceptual models and results chains. If you're familiar with the open standards of conservation, results chains framework. So that really benefited, that information, kind of just conceptual models of our understanding of the system that were developed by scientists and stakeholders in the region. That really benefited the qualitative network model. But as data stewards who are working with numerical data, the integrated model suite, I guess one of the big challenges there has been getting data of across multiple, the Puget Sound is a very large area. There are lots of jurisdictions. And so the accessibility to data across multiple jurisdictions and across the Puget Sound watershed has been a real challenge. So kind of synthesizing data sets from multiple sources that might have slightly different data structures, or access is limited in certain ways in certain areas versus others. So there are definitely challenges of the kind of synthesizing these data sets across a really large spatial scale. So that's definitely been a challenge. Just an example, although this might not be super relevant to all of you, but the land cover change model, which was projecting land cover changes, the modeler tried to obtain zoning information across all of the jurisdictions, but that information is contained in different ways, different definitions, and different kind of parcel scales or grid sizes across all of the different jurisdictions, and ultimately just became too much of almost an impossible task to align those across all of the Puget Sound watershed. So ultimately had to kind of use other information besides zoning. But yeah, there are probably other examples like that where just accessing data at this scale in a comprehensive and kind of cohesive way was really challenging.
I imagine so. Graeme, I see your hand up.
Hi, yeah, just it's not more of a comment rather than a question, but that Q&M looks really useful for us actually in terms of I showed you the the decision support tool we have. All of our controls are very much like, changing the mortality on a stage, and a lot of the managers say to us when we go to them and show them the tool, they say, but what action causes that? And we always bat that back to them and say, well, that's your job. Hey, you need to figure out what actions on your system will have that effect. But the Q&M looks like a really great way to maybe kind of bridge that gap for us in terms of if we lay out all our mortalities as nodes, and then around it lay out all the management actions, and then just connect them all with positive and negatives, and or bi-directional like you've done there. I think that's really fascinating. So yeah, just a comment. I think I'm going to pass this on to my my modelers and say, look at this.
Yeah.
Really
yeah. Thanks so much, Graeme. Yeah, I think the qualitative network model is such a adaptable tool, and has proved really useful for us because it is so adaptable and flexible, and you can kind of define the scope of your question and your problem and your system, and then evaluate your assumptions of the system behavior, essentially. And a qualitative network model that might be really interesting for you to look at, Graeme, was developed by Catherine Sobocinski for the Marine Survival Project in Puget Sound, which was looking at early marine survival of salmon and the factors kind of influencing that. So I'll try to pull up the link quickly and drop that in the chat for you, but I would recommend taking a look at that.
Thanks. Yeah, that would be really useful, that link. Thank you very much.
Yeah.
Awesome. Happy that this is inspiring some folks. Go ahead, Robert.
Thanks. Thanks, Caitlin. For to the note to give us a description of how.
Hey, Robert, we're having a hard time hearing you. It's pretty quiet.
Yeah.
I'm sorry.
Oh, there you go. Way better.
Microphone. And I apologize for my ghastly appearance here. The sunshine is out here on the Kitsap Peninsula. Anyways, you described nodes on beneath those are elements that create a score from -0 to 1. You went through a process then for each of those elements that would come up with a combined score from -1 to 1. How did you initially calibrate those elements that will make up the score for the node?
Yeah. I think I understood your question, but let me know if this doesn't get it quite right. But so the software, which is essentially an R package called QPress, which is an R package for doing this qualitative network modeling, that randomly assigns. So the network is simulated many thousands of times, as many as you tell it to, and typically people use 10,000. So 10,000 versions of the network were created with randomly selected interaction strengths. So I didn't tell the software at all kind of what the interaction strength would be. We allowed that to vary randomly. That being said, the system does compare those networks to stability criteria. And so in certain cases, if interaction strengths that were randomly selected resulted in a network that was unstable, that version of the network was discarded. So we ended up with 10,000 stable iterations of the network using randomly selected interaction strengths. There are other versions that are kind of this approach that are similar, like fuzzy cognitive mapping, or FCMs. In that case, you can select interaction strengths, but you don't get the kind of uncertainty analysis that you get with using the randomly selected interaction strengths from QNMs. But if you were really certain that an interaction strength should be 0.7, then you could assign that value in kind of different versions. And there's some new, QNMs are gaining traction in a really cool way in ecology. And so there are some really good examples where people have imposed certain rules in cases where they were very certain about the interaction strength. Or like, I only want to take networks that have an interaction strength for this particular link that fall between this number and this number, because I'm very certain that this is a strong interaction, for example. And I only want to look at versions of the network that represent that.
That's got it. Thanks.
Okay, great.
And
good.
Thank you for the information in the chat to ResearchGate.
Oh, yeah.
All right.
Yeah,
excellent.
thanks for sharing that, Scott.
Yeah, I appreciate that, Scott. All right, I think we've got a few minutes left, so I'll hand this back to Sam to wrap it up. But I just wanted to say a big thanks to all of our presenters today. I think this was a fantastic session, and I think a lot of really good information was shared. So thank you. We appreciate you guys. And go ahead, Sam.
Yeah, thanks everyone for who presented today and who attended. I also wanted to give a big thank you to our ETIS Planning Committee. This has been over a year in the process, and so every one of these people have helped immensely, and it's been a good push forward. One last thing. Next week we have our second session, which will be on artificial intelligence and machine learning. It's at the same time. You can go to the pnamp.org website and go to our events and RSVP for this event. Some of you did that for the event today. But yeah, should be another great set of presentations. So yeah, join us next week. And again, this recording will be available on the PNAMP YouTube channel later, probably this week. So look for that.